Welcome. In this video, I'm going to estimate and interpret binary logistic regression model in R. And in this video, I'm using simple binary logistic model in which the dependent variable will be a categorical variable having two categories, and my independent variable will be a quantitative variable. In another video, that is in a separate video, I'll also run and estimate simple binary logistic regression in which my dependent variable will be categorical having two categories, and my independent variable will be categorical variable. And finally, in another video, I'll run a logistic regression of a categorical variable on a number of categorical and quantitative variables. To do that, let me remind you, in R, the binary logistic regression can be estimated with the GLM function, and the family is equal to binomial argument. So we will use this argument, GLM as well as binomial argument. Just like linear regression, the formula used inside the function must be written as a dependent variable phi by tilde, and then a list of independent variables in this order. While the dependent variable must be categorical with two levels, the independent variables can be of any type. However, interpretations differ depending on whether the independent variable is quantitative or qualitative. For completeness, we shall illustrate this type of regression with both a quantitative and qualitative independent variable, starting with a quantitative independent variable in this video. For these illustrations, we will use the heart disease dataset, which is available in R package by the name KMED. This data frame consists of 14 variables, of which 5 will be retained for this analysis. And these 5 variables include age, where age is measured in years. Then we have sex, either male or female. And then chest-pain type is another variable. It has 4 categories: 1 for typical angina, 2 for atypical angina, 3 for non-angina anginal pain, and 4 for asymptotic pain. Finally, we will have another variable that shows maximum heart rate achieved. And then one more variable is that of class, that is class diagnosis of heart disease. It is divided into 4 classes: 0, 1, 2, and 3. However, the last variable will be recoded into 2 categories, and 0 will stand for no disease, and 1 stand for heart disease. So I'll recode it in a way that 1, 2, and 3 means that there is heart disease. Suppose we want to estimate the impact of patient's age on the presence of heart disease. How can you do that? In this case, age will be our independent numeric variable or quantitative variable, and heart disease will be our dependent variable, and it has 2 categories. 0, it stands for no disease, and 1 stands for disease. After this, I'll go to R, and this is R. As you see, I have already downloaded my data file that is named as DAT, and this data set has, as I mentioned earlier, 5 variables, and there are 297 observations. So here is this data set. Age is measured in years, sex male female, categorical. Chest pain, this has 4 categories. This is quantitative variable, maximum heart rate achieved, and this is a dependent variable which is categorical, either having heart disease or doesn't have heart disease. So after that, I'll use this as my dependent variable, and in this video I'm using age as my quantitative variable. So this is how I will estimate or run binary logistic regression model. I will name this model as M1, and I'll give this command GLM because a binary logistic regression model is estimated with GLM function, and within parentheses the dependent variable heart disease, and tilde it will be regressed on age. Age is a quantitative variable and the data set is dead and the family is binomial. So if I click run, the model has been estimated. After this, I would like to summarize the results of this binary logistic regression model, in which my dependent variable is heart disease and my independent variable is age. So let me do it again. Let me see summary, and my model is M1. Let me check if it is done or not. So here is my model, and in this model you can see that the coefficient of the age is 0.05291, and the estimated coefficient of the constant is minus 3.05. Now coefficients are slightly harder to interpret in logistic regression than in linear regression, because the relationship between the dependent and independent variable is not linear in case of a logistic regression model. So what does this mean? So this coefficient means, since the dependent variable is log odds, so this means that with 1 unit change in age, the log odds change by 0.0529. Now this is a little bit difficult to interpret and understand. In order to understand this, we need to convert this to, but one thing is sure, that the older the person, the more likely he or she is to develop heart disease. So we know the direction of change. So there is a positive relationship between the age of the respondent and the likelihood of his developing heart disease. In order to quantify this positive relationship, we will have to calculate odd ratios, and to do that I'll use this command e raised to the power coefficient of this model, that is age. So if I do that, it will give me odd ratio of 1.05. So let me try it, and it has now been estimated as 1.05. 1. Sorry, it should be this one, this one. So the coefficient has now been, the odd ratio has now been estimated. If you remember, the coefficient of age in the original model was equal to, 0.05291, but when I converted that into odd ratio, then the odd ratio for this coefficient is equal to 1.054. Now based on this result, we can say that an extra year of age increases the odds, that is the chance of developing a heart disease, by a factor of 1.054. Therefore, the odds of developing a heart disease increases by 1.054 minus 1 multiplied by 100, that is equal to 5.4% when a patient becomes 1 year older. So it means that with every 1 year increase in the age of a person, the chance of a person developing a heart disease increases by 5.4%. Now let us suppose I would like to predict the probability of developing a heart disease for a patient of 30 years old. So I want to see what is the probability of a person who is 30 years old based on the results of this model. So the command is spread. Spread is for prediction, and this is the argument predict from this model, that is M1, and then comma new data is equal to data frame, and age is equal to 30, and type response. So if I click on this, it will predict the probability for me. So let me highlight this all and predict the probability from now if I click run, now it means that it is predicted that a 30 years old patient has 18.79 probability of developing a heart disease. Since this is the probability is equal to 0.1878. If you use the same formula, 1 minus 0.187 multiplied by 100, so it means that it is predicted that a 30 years old patient has 18.79, almost 19% chance of developing a heart disease. Now let us suppose I want to see what will be the probability of a 50 years old person to 50 years old person to develop heart disease. Since the probability of a 30 years old patient to develop heart disease was 0.18, I will see whether the probability will be higher for the for a person of 50 years age. So yes, now this probability increased from 0.187 to 0.399. So it means it is predicted that a 50 years old patient has 39.98% chance of developing a heart disease. That is almost 40% chance of developing a heart disease. Similarly, if we want to calculate or compute probability for a person of 90 years age, so I will predict that this probability will be much higher as compared to 30 years old or 50 years old respondent. So if I click run, it will give me the chance of a 90 years old patient to develop a probability. So you can see this probability now increased to 84.68%. So now it is predicted that if a person is 90 years old, he has 84.68 chance of developing a heart disease. So this is how we can compute probabilities that change with the age of the respondent. So as I mentioned in this video, I used a simple binary regression model in which my dependent variable was heart disease, and it had two categories, that is 0 is equal to for no heart disease and 1 for heart disease. So it was a categorical, binary categorical variable, and my independent variable was age, and it was a sensible result based on this model prediction that the probability of developing a heart disease increases with age. And I showed that with the help of this model. For a 30 years old age, the probability was 0.18. For a 50 years old age, the probability was 0.39, almost 0.4. And for a 90 years old patient, it was almost 0.85. So it means that the chance of developing a heart disease increases with the age. So this is very informative and very interesting results. I hope it was quite useful for you. Kindly share this video with your friends, with your colleagues, and with your students, and subscribe to the channel. Don't forget to click on the bell icon so that you can get timely notifications about my other videos that I'll upload for you. Thank